My name is Justin Duchatelier, and my research partner's name is Tyler Holmes. We are undergraduate research assistants at Kennesaw State University in the Computer Science Department. Our research analyzed the effects of thermal attacks on edge computing devices. Edge computing is a distributed computing topology in which data is processed locally that would allow for better response times and decreased bandwidth. Because they are newer hardware devices, the current research on edge devices is limited. We aim to expand on the available research for edge devices. Further, over 99% of the power used in high-performance computing is output as heat. Excessive heat will damage hardware, and covert thermal attacks can go undetected. This will eventually cause imminent failure. Our research question is, how well do edge devices perform when they experience excessive temperatures? We performed several experiments on 3 different edge devices. We observed their performance during a simulated thermal attack. You can see the different experiments that we performed on this slide summarized below. There were 4 different experiments. The first compared the different cooling configurations. The second looked at the power consumption and temperatures during the thermal attack. The third compared the temperatures during throttling when the CPU was throttled at various maximum set frequencies. And the fourth experiment showed the CPU frequency and temperature readings that were recorded while executing AI benchmark. Each of these tests, except for the final 4th test, used a stress test to simulate a thermal attack. The list below contains the hardware and software we used for our experiments. We ended up primarily using the Raspberry Pi 4B, and we also used the Google Coral and NVIDIA Jetson TX2. Our results demonstrated that lower frequencies experienced lower decreases in performance when the CPU was throttled. Also, power consumption and temperatures should be actively monitored because thermal attacks have a similar heat signature and power consumption trace to normal yet compute-intensive workloads. Finally, we found that there is a negative correlation between the CPU frequency and the temperature. As the CPU frequency goes down, then the temperature can be found to be increased. As the temperature is not as high, then the CPU frequency will increase. This slide shows 2 of the different experiments that we performed. The figure on the left is a graph that contains the throttle temperatures of the Raspberry Pi when there were various maximum set frequencies ranging from 600 megahertz to 1500 megahertz. The figure at the right is a graph of the different cooling strategies and the temperatures that were achieved with the stress test versus different cooling systems as passive, active, static, and active dynamic, versus when there was actually no cooling, meaning the heat sinks and fans were not active nor present in the system. This final slide shows the consumption of the power and the temperature readings of the thermal attacks that we simulated. On the far left, you'll see what the monitoring status was when the attack was not present. And now in the middle, you'll see what the monitoring status was while the thermal attack was being executed. The far right shows the results of the AI benchmark and how there's a negative correlation. As the temperature increased, the available frequency decreased. And as the frequency was able to achieve a higher frequency, the temperature reading was lower.